Okay, so last class session, we developed this idea of drawing Lewis structures via analogy using isoelectronic atoms and ions. So let's take a look at carbon dioxide and let's try to draw a Lewis structure of carbon dioxide from scratch. So first, carbon contributes how many electrons? Carbon contributes how many valence electrons? 4, yep. Carbon contributes 4 electrons. How many electrons does oxygen contribute to our total number of valence electrons? 6, okay. And we have 2 oxygen atoms. So we have 4 plus 12, that gives us 16 electrons to work with. Now what will our central atom be? What is our least electronegative non-hydrogen atom? Carbon, yep. So we put carbon in the center and we surround it with both oxygens. Wonderful. Next thing we're going to do is we're going to form 1 bond each. So we lose 2 electrons per bond. So 2 and 2 is 4. We have 12 electrons remaining. Now, which atom do we start placing our lone pairs on? Do we place our lone pairs on carbon first or oxygen first? Do we place our lone pairs on the inner or outer atoms? Oxygen, your outer atoms. And this oxygen needs 6 electrons for a complete octet. And the oxygen on the left also needs 6 electrons. So we've used up 12 electrons. We have 0 remaining. Now my question to all of you is, does this central carbon have a complete octet? Does the central carbon have a complete octet? No. So we're going to convert a lone pair into a double bond. Okay, does this carbon have a complete octet? No, so we'll repeat this process by converting a lone pair into a double bond. At this point, if you're paying attention and thinking through what's being done here, you may notice that I've done something implicitly that is really important to consider. So why did we choose to have 2 double bonds rather than a triple bond and a single bond? Would someone like to take a look and explain why the structure on the left is preferred for carbon dioxide? So why? What's the reasoning? So when we discussed favorable and plausible Lewis structures, we brought up this idea of formal charges. So one thing I'd like to ask is, if you think about the formal charges in the structure on the left versus the structure on the right, which structure has the smaller formal charges? Which structure minimizes formal charges? The structure on the left with formal charges of 0, 0, and 0, or the structure on the right with a formal charge of -1, 0, and +1. Which structure has the smaller set of formal charges? The structure on the left, right? Exactly. So keep in mind that if you have a choice between 2 potential structures, draw them both and look for the structure with the smallest formal charge, or the structure that places positive formal charges on less electronegative atoms and negative formal charges on more electronegative atoms. Okay, so let's take a look at an example, and this one should be fast. Let's look at NO2+. So I'd like you to take a moment, and if you look up in the Zoom interface tab, you'll see a little pen key called annotate. If you want, I'd like someone to try and share their proposed structure using the annotate function. I'll give everyone about 3 minutes to work on this problem, And at the bare minimum, I'd like to see in the chat some electron counting, some indication of the central atom. But if someone wants to try to use the annotate tool to draw a structure, which is found in the Zoom tab, you're more than welcome to. If not, we'll discuss in about 2 to 3 minutes. And remember our idea of isoelectronic atoms. And don't be shy to message me your proposed electron counts and your proposed central atoms. And we'll discuss in about 1 minute. Okay, so there are two ways of looking at this problem. First, if we compare carbon and nitrogen plus, do carbon and nitrogen plus have the same number of valence electrons? Let's think. How many valence electrons does carbon have? How many valence electrons does carbon have? 4. And nitrogen normally has 5 electrons, but since we have a +1 charge, we subtract 1. So nitrogen plus also has 4 valence electrons, if you're thinking about an ion as just a single species that you can count electrons for. So then, because carbon and nitrogen have the same number of valence electrons, you can just as easily take carbon in this Lewis structure and replace it with nitrogen plus. Now, the beautiful thing about this method is that it also gets the formal charges right. You don't even have to do a second calculation. So that's why I like this method personally. It just requires a little bit of careful thought. So both of these atoms and ions have 4 valence electrons. Now, of course, if you want to draw these structures from scratch, you're more than welcome to. So NO2 plus, nitrogen contributes 5 electrons. Oxygen contributes 6 electrons, and we have 2 of them. So we have 5 plus 12. And what do we do when we have a +1 charge? Do we add or subtract from our electron total? Do we add or subtract from our electron total? Subtract. So we subtract 1, and that gives us 16 electrons to work with. So what is our central atom going to be? What is our least electronegative atom going to be? Nitrogen. Perfect, perfect. So we put nitrogen in the center, we surround it with 2 oxygens, and now we form 1 bond each. So we used up 4 electrons. We have 12 electrons remaining. This is starting to look a little similar to what we've done before. Now, where do we place these 12 electrons? Where do we place our 12 electrons? On our outer or inner atoms? On oxygen or nitrogen? Where do we place our lone pair electrons first? oxygen. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We now have 0 electrons remaining. Now we ask the question, does nitrogen have a complete octet? Does nitrogen have a complete octet? No. So we'll convert a bond. We'll convert a lone pair into a bond. Does nitrogen have a complete octet? Second time. Still no. So we convert a lone pair into a double or triple bond. Now we do have to assign formal charges. So let's go through that calculation. So in terms of the formal charge of oxygen, we have our group number, which is 6. How many bonds is the oxygen on the left forming? 2. Okay, and how many lone pair electrons? How many dots do we see? 4. Yep. So we have a formal charge of 0. Now, if we look at the oxygen on the right, does the oxygen on the right have the exact same bonding pattern? Does it have the exact same bonding pattern? Yes. So then its formal charge is going to be what? 0. Yeah. So no need to think about when you're repeating the same calculation multiple times. If it has the same exact bonding motifs, it will have the same formal charge. Okay, let's now talk about this central nitrogen. So the formal charge is equal to the group number, which is 5. And how many bonds is this nitrogen forming? 4, yep. And it has 0 lone pair electrons, so we have a formal charge of +1. So our final structure for nitrogen, well, for the following cationic species looks like this. Any questions on this example? So you notice if you draw your structure via analogy, it's pretty fast compared to the from scratch method. You're welcome to use either method, whatever you're most comfortable with. Both will get you to the same answer. But, and this is really important, your Lewis structure needs to include formal charges. If it has the incorrect formal charges, you'll lose points on these questions. So just make sure you're being meticulous. Any questions on this? Okay, let's keep going now. So structures with the same formula in which the atoms are bonded in a different arrangement or connectivity are known as isomers or constitutional isomers. So for example, CH3CN has multiple plausible Lewis structures, each representing a constitutional isomer. So if I make my pool of electrons, carbon contributes 4 electrons and we have 2 of them. Hydrogen contributes 1 electron and we have 3 of them. And nitrogen contributes 5 electrons. So we have 8 plus 3 plus 5, which in turn gives us 16 electrons to work with. Now in terms of our skeleton, we're going to have 2 central atoms. One of our carbons is going to be surrounded with 3 hydrogens and a carbon, and the other carbon will be surrounded with a nitrogen. We're then going to form 1 bond each, just like always. So we formed a total of 5 bonds. So now we have 6 electrons remaining. So what atom in this structure has an incomplete octet? Where do we place our lone pairs first? Where do we place our lone pairs first? What's our most electronegative atom? Nitrogen. So let's dump these 6 electrons on nitrogen. Okay, and now let's do a check. Does this carbon on the left have a complete octet? Does the carbon on the left have a complete octet? Yes. Does this carbon in the middle have a complete octet? No. So then let's convert a lone pair into a bond. Now do we have a complete octet? How about now? No. Okay. So let's convert another lone pair into a multiple bond. Now we have a complete octet. So let's draw out our final structure. So this is just one potential structure for CH3CN. Now, you can, of course, change your skeletal connectivity. So for example, we can swap the nitrogen and carbon. Notice how these two structures are constitutional isomers because one, they have the same formula, but they have different connectivity. Does everyone notice how the connectivity, the order that the atoms are connected, bonded to each other, is different? Does everyone see how the connectivity is different? Okay, so you can even get more creative with your constitutional isomers, and you can produce really weird species. Like this, for example. Notice the main thing I want you to be able to do is to identify pairs of molecules as constitutional isomers if you're given a pair. Okay, so there's another type of isomer which is more important in organic, but nonetheless, it's pretty interesting to talk about now. Structures with the same formula in which the atoms are bonded with the same connectivity, but with a different 3D shape, are known as stereoisomers. So for example, dibromoethylene has both constitutional isomers and stereoisomers. So let's do a count. Let's count our electrons. Let's make some structures from scratch and let's prove this to ourselves. So bromine contributes how many electrons? Bromine contributes how many electrons? 7, okay. We have 2 bromine atoms, wonderful. Carbon contributes 4 electrons. We have 2 carbon atoms. Hydrogen contributes 1 electron, and we have 2 hydrogens. So adding these up, we have 14 plus 8 plus 2. That in turn gives us 24 electrons. So we're going to place our carbons preferentially as the central atoms, and then we're going to surround our carbons with each of our remaining substituents. In general, carbon wants to form up to 4 bonds. Now, you may ask, why don't we put 3 substituents on one of our carbons? Well, we can entertain that possibility and we can see what happens. So we'll just keep this possibility off to the side and we'll focus on drawing our main structure for now. So with our 24 electrons clearly established, we're going to form 1 bond each. 2, 4, 6, 8, 10. Okay, we have 14 electrons remaining. So where are we going to place our electrons first? Where are we going to place our electrons first? What are our most electronegative atoms? Bromine, yep. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we've used up 12 electrons. We have 2 electrons remaining. Now, what atom does not have a complete octet that needs additional electrons? Carbon, exactly right. So we're going to take this lone pair and put it on carbon. Carbon traditionally doesn't like lone pairs, but this is just a formality for now. And that lone pair is not going to stick around for very long. Now, Looking at this carbon on the right, does the carbon on the right have a complete octet? Does the carbon on the right have a complete octet? No. So we're going to take one of our lone pairs, and in general, you prefer using lone pairs on the least electronegative atom, and we're going to form a double bond. Now, does this structure have a complete octet? Yep, so this structure is perfect. So to look at this at the structure on the right, where we presupposed that, where we tried to think about changing our connectivity and putting 3 substituents on one carbon, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have used up all of our electrons, but this carbon has an incomplete octet. So this structure is a no-go from the perspective of the octet rule. You don't have enough electrons to work with, your formal charges are bad, and there's no way, if you put 3 substituents on one carbon, to get a reasonable structure that follows the octet rule. Does that make sense to everyone? So you notice by trial and error immediately if a structure is not viable, because you'd end up with a bunch of incomplete octet structures or really terrible formal charges. Now, there's another way, so looking at this structure, we can now draw a constitutional isomer. So let's look at a constitutional isomer. So we have the same formula, but a different connectivity. So instead of having both of the bromines on the right-hand side, I'm gonna have one of the bromines on the left and the other on the right. So this is a constitutional isomer. So these two compounds, these two molecules are constitutional isomers. Does everyone see the fact that these molecules have the same formula, but a different connectivity? Now, in terms of stereoisomers, so a stereoisomer has the same connectivity, but a different shape. So in this case, okay, do you notice how both of the bromines are pointing quote unquote up? Well, in one of the stereoisomers, we'll have one of our bromines pointing up. They're still attached to the same carbon atoms, and the other bromine pointing down. So these two compounds are stereoisomers because they have the same connectivity but a different shape. Does everyone notice how the bromines are attached to the same carbon, but they're arranged in 3D space in different ways? These two molecules have slightly different shapes. Does this make sense to everyone? Okay, perfect. So let's look at another set of two compounds, and these ones are quite interesting. First things first, let's look at carbonate anion, which is CO3 2-. Let's do some electron counting. So carbon contributes 4 electrons. Oxygen contributes 6 electrons, and we have 3 oxygens. So we have 4 plus 18. Now what do we do with this 2- charge? If we have a negative charge, do we add or subtract electrons from our total? Do we add or subtract electrons? We add. So we add 2. We have 24 electrons in total. What is our central atom? What is our central atom in this case? Carbon, yep. So we're going to surround it with our 3 oxygens and form 1 bond each. So we lose 6 electrons. We have 18 electrons remaining. Now my question to you is, how many electrons do each of our oxygen atoms need? How many additional electrons do each of our oxygen atoms need? Not total, additional. How many do I need to add? 6. Yep. 2, 4, 6, 8, 10, 12, 14, 16, 18. Lo and behold, we're out of electrons. Now, does this carbon have a complete octet? No. So we're going to take one of our lone pairs and arbitrarily move it down. Now let's calculate formal charges. This is a charged molecule, so by definition, some of our atoms must have a charge. So let's look at the formal charge of this oxygen. We have our group number 6. How many bonds are we forming? 1. Okay, and how many lone pair electrons do we have? 6. Okay, that gives us a formal charge of -1. So we have a negative formal charge here and a negative formal charge here. How was I able to do that again? Do both of these oxygens have the same bonding pattern? Do both of these oxygens have the same bonding pattern? Yes. Ergo, their formal charges are going to be the same. Okay, so this is wonderful so far. So we have a nice structure, and just to be 100% correct, we need to put this structure in brackets and put a 2- charge. Now, you may have asked, and this seems a little silly at first glance, but why did we form the double bond up here? Is there any reason why we formed the double bond with the top oxygen? Is there any particular reason? Is there any reason why the structure that we've drawn is better than, for example, the following structure? Is there any particular reason, or do these structures look almost identical to you? Is there any, in terms of the rules that we've discussed, is there any potential reason? They're almost identical, right? There's no particular reason why you can't draw out this as a valid structure. Now, these two structures are related, and these two structures are known as quote unquote resonance structures. We'll expand on this concept right after this next example, but these two structures are a special class of related structures known as resonance structures, which are multiple ways of depicting the distribution of electrons in the same molecule. Now, to help drive home this idea of drawing Lewis structures for anionic species, I'd like you to try and draw out a valid Lewis structure for NO3-. You're welcome to use the isoelectronic atom method or the atom substitution method, or draw the structure from scratch. Make sure you assign the formal charges in your structure, and I will give you about 3 to 4 minutes. And don't be shy to message your proposed electron count or use the annotate tool to try to draw out a proposed structure. Otherwise, we'll discuss in about 3 minutes. Yep. The electron counts I've received so far look good. I'd like you to continue drawing out your structures, and then we'll discuss in about 2 minutes. and we'll discuss in about 1 minute. Okay, so let's discuss this example. Well, just like before, you can think of substituting and comparing carbon and nitrogen plus. Both of these species have 4 electrons. So you can just as easily take your structure for carbonate, which is CO3 2 minus. You can replace the carbon with a nitrogen plus. And that in turn gives us NO3 minus, or nitrate. That's one method of doing it. That's pretty fast if you use the isoelectronic method. But let's pretend we'll draw it from scratch. So nitrogen contributes 5 electrons, oxygen contributes 6 electrons, and we have 3 oxygens. So we have 5 plus 18. We have a -1 charge, so we add 1. So now we have 24 electrons to work with. We put nitrogen as our central atom and we surround it with 1 oxygen each. We then form 1 bond each, so we used up 6 electrons. We have 18 remaining. Next, we add our lone pairs to each oxygen atom. Now, we've run out of electrons. My question to you is, does this central nitrogen have a complete octet? No. So we're going to take one of our lone pairs. Oops, I accidentally got rid of the oxygen too. We're going to take one of our lone pairs and we're going to convert it to form a double bond. Now the nitrogen has a complete octet. Now let's calculate the formal charges. So the formal charge of this bottom oxygen is 6 minus 1 minus 6, or -1. What is the formal charge of this rightmost oxygen? -1, exactly right. Okay, let's look at nitrogen now. In terms of formal charges, we have a group number of 5. How many bonds does this central nitrogen form? 4, yep. And do we have any lone pairs? Any dots on the central nitrogen? No. So we have a formal charge of 1. So then, rewriting our structure in a cleaner way after we've spent all this time calculating our formal charges. Each of our oxygens are negatively charged and the nitrogen has a positive charge. We'll put our entire structure in brackets and assign a negative charge to this entire structure. Perfect. So we touched on this idea that there are multiple ways to draw the distribution of electrons in these molecules. And this really brings about this idea of resonance. So resonance structures are one or more valid Lewis structures with the same skeletal formula, but a different distribution of electrons in bonds and lone pairs. So electrons shared between atoms in double and triple bonds, and electron pairs and atoms adjacent to double and triple bonds are delocalized across atoms that are participating in resonance. So resonance structures are not unique molecules, and they're not even representing the actual distribution of electrons. So these resonance structures are essentially multiple Lewis structures showing different distributions of electrons that obey the octet rule for a molecule. Resonance isn't just rotation. So if we look at carbonate, for example, we can have our double bond on our topmost carbon. Now, I'm just going to put little labels here. 1, 2, 3. Let's just pretend we know each oxygen and we're able to clearly identify each oxygen as a unique oxygen atom. Now, we can just as easily form a double bond with our bottom left oxygen atom. So we shift our electron density, or we can draw a different distribution of electron density. That's a more apt description. And we can form a double bond with our bottom left oxygen. We're not just rotating the molecule. These resonance structures are describing different distributions or different possible distributions of electron density. So they really help us visualize potential ways that electron density can be distributed in our molecule. And if we average these resonance structures, we can get a sense of the relative distribution of electron density in our molecule. Okay, so as we can see, we can draw a total of 3 possible resonance structures. And we represent these resonance structures using these double-headed arrows. So resonance is not rotation of our molecule. We're not just spinning this molecule around. Resonance structures represent different distributions of electron density in bonds and lone pairs across atoms in our molecule. Does this make sense to everyone? Does everyone see how each of these structures have a slightly different distribution of bonding electrons and lone pair electrons? Okay. So now, resonance structures are purely a method of drawing and visualizing different distributions of electron density. The molecule does not adopt a structure of any one resonance structure. The actual distribution of electron density in the molecule and the actual structure we observe in terms of bond length, strength, is a weighted average of all resonance structures based on their stability, following, of course, your formal charge rules. So to highlight this point, I'm going to introduce this idea of bond order. Bond order is the number of bonds between 2 atoms. So let's look at the 3 structures for carbonate, and let's consider the bond order in each case. Okay. So in red, we're going to look at the bond order. So what is the bond order for this carbon-oxygen double bond? How many bonds are shared between carbon and oxygen? 2. Okay, so our bond order is 2. What about for this single bond? What's the bond order for a carbon-oxygen single bond? 1, yep, and 1. Okay, let's look at the formal charges. So we have a formal charge of 0, a formal charge of -1, and a formal charge of -1. We're now going to look at another resonance structure. And we're going to consider the formal charges. Whoops, sorry about that. We're going to consider the formal charges and bond order in this structure. So as we notice, if we look at our top carbon-oxygen bond, what is the bond order in our second resonance structure? What is our bond order? 1, okay. Here, for our bottom right carbon-oxygen bond, we have a bond order of 2. For our bottom left carbon-oxygen bond, we have a bond order of 1. We're just counting the number of bonds between our atoms. Okay, now in terms of formal charges, this top oxygen now has a formal charge of -1. We have a formal charge of 0 in the bottom right and a formal charge of -1 in the bottom left. Now there's one more unique resonance structure. Now, looking at our bond orders, again, we have a bond order of 1, 1. And what is the bond order for this bottom right carbon-oxygen bond? Oh, sorry, for the bottom left, sorry. For the bottom left carbon-oxygen bond, the bond order is 2. Okay, in terms of formal charges, we have a formal charge of -1, -1, and 0. Okay, so if you want to determine the average, so if we want to determine the average carbon-oxygen bond order, and let's look, we have to look at each carbon-oxygen individually. Let's look at the average carbon-oxygen bond order for the top carbon-oxygen bond, okay? So we're focusing in on this top carbon-oxygen bond. So we take the bond order in our resonance structure number 1. So our average bond order we add up our bond order from each of our 3 structures, and then we divide by the total number of resonance structures. So what's the bond order in structure number 1? What's the bond order in our first resonance structure? 2. Okay. What about the second? It's 1. And in the third, the bond order is 1. We're looking just at this top carbon-oxygen bond. You have to look at each bond step by step. Now we divide by the total number of resonance structures. How many structures have we drawn? How many structures have we drawn? 3. So this gives us a bond order of 4/3. So what this is saying, it is stronger than a single bond, but it's weaker than a double bond. Additionally, we can also calculate the average oxygen formal charge for our top oxygen. So looking at our top oxygen atom, all we have to do is add up the formal charge at each of our resonance structures and then divide by our total. So what are our formal charges for our top oxygen in these 3 structures? What are our formal charges? Let's list them. What are the formal charges for our top oxygen? In the first structure, it's 0. What about in the second structure? In the second structure, -1. Third structure, -1. So we add up our formal charges and then we divide by the total number of structures. So we have 0 plus, well, 0 minus 1 minus 1. And we divide by our total number of structures, which is 3, and that gives us a formal charge of -2/3. So what this is saying is that each of our oxygen atoms, on average, has a negative charge, but it's not quite the same as a full -1 charge. It's a delocalized charge. Okay, does this idea make sense to everyone? Of calculating average bond order and formal charge? Now, in terms of how we represent our average structure in terms of how we'd represent our average structure. So in average, if we want to draw a resonance hybrid, which is the average of all of our resonance structures, we draw out each of our carbon-oxygen single bonds, but instead of showing a formal double bond, we draw these dashed lines. And these dashed lines are essentially saying that we have a 4/3 bond. Likewise, if we look at the formal charge of each of our atoms in the resonance hybrid, this atom in the resonance hybrid would have a formal charge of -2/3. So the resonance hybrid is the average of all of your resonance structures, accounting for weighting, of course, that has an average bond order, bond length, bond strength, and formal charge for each of its bonds that are averaged among all of your resonance structures. Does this idea of a resonance hybrid make sense to everyone? We've essentially taken all of our average data for each of our carbon-oxygen bonds and each of our formal charges on each of our atoms, and we've drawn a structure that tries to reflect this average. So this resonance hybrid is what you'd actually see. This is probably the most accurate description of the quote unquote true structure, or the structure that we'd actually see in terms of bond length, bond strength, and charge distribution for our molecules. Okay, so I'd like you now to take a moment and to apply this idea of drawing resonance structures, and I'd like you to draw the reasonable resonance structures for nitrate, and I'd like you to guess and tell me after calculation what is the bond order for the nitrogen-oxygen single bond. So we'll take about 4 to 5 minutes to discuss this example, and then we'll come together as a group to discuss. And don't be shy to message me your proposed response for the bond order for the nitrogen-oxygen bond. So this will require drawing each of your structures, looking at the resonance structures, and then calculating the average bond order. And we'll discuss in about 3 minutes. and we'll discuss in about a minute and a half. Don't be shy to message me your proposed response for the average bond order. Okay, so let's talk about this next example. So we already know we've drawn the structure for nitrate previously. Nitrate looks something like this. Okay, so in terms of drawing resonance structures, all we are doing is moving our electron density in our bonds to lone pairs and from our lone pairs to a bond. The way I like to think about drawing resonance structures is I push my electron density down from a lone pair to form a bond, and as a result, the electrons in a double or triple bond get pushed up to form a lone pair. Using the method of pushing electrons always ensures that you're following or at least trying to follow the octet rule, and it avoids issues associated with accidentally drawing structures that are incorrect when you're drawing resonance structures. So again, you kick your lone pair down to form a double or triple bond, and your double bond gets kicked up to form a lone pair. So just like carbonate, almost exactly identical to carbonate in that matter, we have the following set of 3 resonance structures. Okay, let's look at the bond order. Let's look at the bond order for the nitrogen-oxygen bond, and let's look at the bottom right. It's completely arbitrary, but let's just pick one of the bonds. So in terms of our bond order, okay, what is the bond order in this first structure? In the bottom right, what is the bond order in the first structure? 1. Okay, what about in the second structure? 2. Okay, what about in the third structure? 1. Okay, so we're going to add up our bond orders, and then we're going to divide by the total number of resonance structures. So how many total resonance structures have we drawn? 3. So that in turn gives us a 4/3 bond order. So if we were to draw a resonance hybrid, the best description that we would have for nitrate we'd use the dashed bond notation to indicate the fact that this bond is a 4/3, a quote-unquote 4/3 bond. It's stronger than your typical single bond, but it's certainly weaker than a double bond. Does this make sense to everyone? Does this idea of drawing resonance structures via arrow pushing and counting average bond orders make sense? Again, just to reiterate, resonance structures are ways of depicting different distributions of electron density in the same molecule. They have the same connectivity and the same shape, just a different distribution of electrons in single and double bonds. So a key signpost that you can draw valid resonance structures is when you have lone pairs adjacent to double or triple bonds, or when you have adjacent double or triple bonds for that matter. Does this idea of resonance structures and calculating average bond order make sense to everyone so far? Is everyone comfortable with these examples so far? Any questions? If we don't have any other questions, let's continue on and let's take a look at an example where we're asked to draw a Lewis structure, a constitutional isomer, and resonance structures. So let's look at the following. Thioisocyanate, okay. So let's start from scratch and let's count our electrons. How many electrons does sulfur contribute? How many electrons? Sulfur contributes 6 electrons. How many electrons does carbon contribute? 4, yep. And nitrogen contributes 5 electrons. So we have 6 plus 4 plus 5. We have a -1 charge. So what do we do to our total? Do we add or subtract 1? We add 1. Okay, and that in turn gives us 16 electrons. So what is our central atom going to be? What's our least electronegative atom? Carbon, yep. So we're going to take our carbon atom and we're going to surround it with a sulfur and nitrogen and form 1 bond each. So we've used up 4 electrons. We have 12 electrons remaining. Now my next question to you is, where do we start placing our lone pairs? On our outer or inner atoms? On the outer or inner atoms? Outer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've burned through our electrons. Now does carbon have a complete octet? Does carbon have a complete octet? No. Okay, so we're going to convert a lone pair into a bond. Does carbon have a complete octet? Once again. No. Okay, so let's convert another lone pair into a bond. Okay, so now here's one valid structure for thioisocyanate. Now, when we say constitutional isomer, what are we saying? When I'm asking you to draw a constitutional isomer, what is different in constitutional isomers? What is different? What is different? If I have 2 constitutional isomers, so what is different about constitutional isomers? What is the key feature? They have a different, and don't be shy to respond in the chat. Constitutional isomers have a difference in what? By bonds, so for example, would this be a constitutional isomer? Is this a constitutional isomer? Is this structure that I drew here a valid constitutional isomer? Or is this structure here? One moment. Or is this structure here a valid constitutional isomer? Let's take a vote in the chat. Which structure is a valid constitutional isomer? The structure on the left, that I'm going to call A, or the structure on the right, structure B? Which one of these structures, and it can be both, which one of them are constitutional isomers? And let's try to get a few more responses in the chat before we discuss this. So in terms of constitutional isomer, so just as a refresher, constitutional isomers have different bond connectivity. So then, if we look at structure A, sulfur is attached to carbon and carbon is attached to nitrogen. So structure A has the same connectivity, so it's not a constitutional isomer. Structure A is a resonance isomer. Oh, well, not a resonance, it's a resonance structure, sorry. Structure B, however, sulfur is attached to nitrogen and attached to carbon. Structure B has a different connectivity of atoms, ergo it's a constitutional isomer. Does this make sense to everyone? So constitutional isomers have a different bond connectivity. The atoms are connected in a different arrangement. For example, sulfur is attached to nitrogen in this structure compared to up here where sulfur is attached to carbon. Does that make sense to everyone? Did that clarify our discussion? Can I get some feedback in the chat just to make sure everyone's comfortable with this? Okay, perfect. Now, in terms of drawing resonance structures, we have structure A to go off of, but let's show the process for drawing resonance structures. Again, you take your lone pair and you kick your lone pair down to form a bond. The double bond then gets kicked up to form a new lone pair. I call this pushing electrons. This is classic and it's something that you'll have to do in organic chemistry. Now, once we pushed our electrons, we have to recalculate our formal charges. So, taking a moment and looking at the following structure, are there any changes in formal charge? Are there any formal charges first and foremost? So we're starting off with a nitrogen with a negative formal charge. Looking at this sulfur, what's the formal charge of this sulfur? What is the formal charge of that sulfur? -1. Yep, the formal charge is equal to 6 minus 1, which is -1. Okay, perfect. So we have two resonance structures for our formula. There we go. Perfect. We're all set. Now, once we have these structures in hand, I'd like you to answer the question, what is the bond order for the sulfur-carbon bond? So let's take about 1 to 2 minutes and calculate the average bond order for the sulfur-carbon bond in these two structures. So remember, when I ask for bond order or formal charge, I'm asking for the average among all resonance structures. So let's take about 1 to 2 minutes and then we'll discuss this in the chat. Given we have both of these resonance structures, all I'm asking is for you to calculate the average bond order, the average number of bonds between sulfur and carbon in each of these structures. And I'd like to see at least a few responses in the chat, so that way we can have a fruitful discussion. Wonderful. So I see some nice responses in the chat. So let's talk a little bit about this. So first and foremost, this bond order. What is the bond order in this resonance structure on the left? What is the bond order in the resonance structure on the left? 2. Yep. Okay. What is the bond order in the resonance structure on the right? 1. Okay. So our bond order for our sulfur carbon bond is 2 plus 1. And how many resonance structures are we looking at? How many resonance structures are we looking at? 2. So it's approximately 3/2. In reality, if we think about the resonance structures and we think about our rules for formal charges, the resonance structure on the left is a greater contributor, as sulfur is more electronegative. Very slightly. These two structures are very close in terms of contribution. So 3/2 is a perfectly valid answer for the average bond order. Wonderful, wonderful. So these are the types of questions that you'll be asked regarding resonance structures. Oftentimes, when you're asked a question where you have to look at resonance structures, you have to draw out full Lewis structures to answer the question fully. Let's keep going now. And let's talk a little bit about expanded octets. So elements with n equals 3, so for the third row and below in the periodic table. So n equals 1, 2, n equals 3. So elements in the third row and below can participate in bonding with expanded octets. So these molecules, so these atoms with n equals 3 and below atoms can form more than 4 bonds. They can accommodate more than 8 surrounding electrons. So let's look at sulfur hexafluoride for a moment. Sulfur, we have 6 electrons. Fluorine, we have 7 electrons times 6. And that in turn gives us 48 electrons to work with. So what is our central atom going to be? What is our central atom going to be? In general, you pick the atom that is the largest for your central atom. So we'd prefer to pick sulfur because sulfur is n equals 3 and below. It's far down on the periodic table, so it can accommodate multiple surrounding atoms. So this sulfur atom can form bonds with up to 6 fluorine atoms. So then, just like normal, we're going to form 1 bond each, and we're going to subtract our 12 electrons, leaving us with 36 electrons remaining. Now, where do we start placing our lone pairs? Where do we start placing our lone pairs? What are more electronegative atoms? Fluorine, yep. So we're going to start placing 6 electrons. So 6, 12, 18, 24, 30, 36. The 12 came from the fact we have 6 bonds, and 6 times 2 is 12. we subtract 2 electrons per single bond. Does that make sense? Perfect. So we used up all of our 36 electrons, and now this structure is perfectly valid. We fulfilled the octet rule for as many atoms as possible, and sulfur can accommodate an expanded octet. So just as a general rule, the large atom is the central atom for expanded octet structures. So in this case, sulfur is our central atom. You can reason that out just looking at electronegativity, but if you need a rule of thumb for expanded octet structures, this is a nice, convenient rule of thumb. Now, let's look at sulfuric acid. Let's look at sulfuric acid, H2SO4. So hydrogen contributes 1 electron, and we have 2. Sulfur contributes 6 electrons, and oxygen contributes 6 electrons, and we have 4 oxygens, okay? So we have 2 plus 6 plus 24, which gives us 32 electrons in total. Now, what's our central atom going to be? What's our central atom going to be? Sulfur, okay? And we're going to surround it with our oxygen atoms. Now, the way that I like to think about expanded octet structures is I first pretend I have to follow the octet rule. So I only surround my sulfur with 4 atoms. Then, if there's no other way, then I start placing additional atoms around my central atom. So I'm going to form 1 bond each now. 2, 4, 6, 8, 10, 12. I have 20 electrons remaining. Now, for those asking, why do I place hydrogens on my oxygens over my sulfur? In general, you place hydrogen, you can think of it very similar to that of a lone pair, and you place your hydrogens on the more electronegative atoms preferentially. You can also invoke formal charges in that discussion. Either way works. Okay, so now that we have our rough skeleton, my question to all of you is, what atoms need electrons? What atoms still need electrons to complete their octet? What atoms still need electrons? Oxygen. So these oxygens that are in the horizontal axis need 4 electrons each, so we subtract 8. And these oxygens that are in the vertical axis need 6 electrons each. So now we're out of electrons. And if you were in Chem 100 and you drew this structure follows the octet rule wonderfully. Now, that's not the actual structure, however, because if we look at the formal charges here, what is the formal charge of this top oxygen? What is the formal charge of this top oxygen in this reasonable structure? What is the formal charge of our top oxygen? -1. Formal charge down here is -1. This is a neutral molecule. Let's look at sulfur. The formal charge is 6 minus 4, which is +2. Now, when we discussed formal charges, does sulfur, which is a pretty electronegative atom, does sulfur really like having a positive formal charge? Does sulfur like having a positive formal charge? Is that good? No. So the true structure of sulfuric acid invokes formal charges, and we form 2 additional bonds. I mean, you can think about it as if it's a resonance structure, and generates the following structure. This structure invokes an expanded octet, but what is the benefit of invoking an expanded octet? When we look at our formal charges, when we look at our formal charges, what is the formal charge on this sulfur now? What is the formal charge on this sulfur? 6 minus 6. We have a formal charge of what? What is our formal charge? What's 6 minus 6? 0. Yep. And the formal charge of our oxygens are also 0. So sometimes we invoke expanded octets in order to minimize our formal charges. So we're at the end of this session. We're going to take a quick 10-minute break, and then we'll finish up this section and this last set of content in laboratory.